Okay, guys, so today we're going to talk about the fundamental theorem of calculus. But before we get into it, I just want to kind of talk to you guys about where the idea kind of comes from. It's not a proof. We're not going to do like a formal proof, but I just kind of want to show you guys what the relationship is there. The fundamental theorem of calculus is trying to help you see. So basically what we're going to do is we have this function g of x, okay, and we've defined it as the integral from 0 to x of 2t dt. And basically, we want to know how to use the fundamental theorem of calculus to work with this problem. But since we don't really know how to do that yet, what we normally do when we're not sure how to work with something is a lot of times you can plot it, you can graph it and kind of get a feel for it, okay? Now remember the definite integral, is defined as the area between the x-axis and the curve. An area below is considered negative, below the x-axis is considered negative, and area above the x-axis is considered positive. So what I'm going to do is I'm going to plot some of these values. So I'm going to take g of 0, I'm going to take g of 1, I'm going to take g of 2, I'm going to take g of 3, I'm going to take g of 4, so on and so on and so on. Okay, so let's see what we get here. Okay, so when I plug 0 in, let me see here. So when I plug 0 in, I'm basically integrating from 0 to 0, right? Because it's g of x, so I'm plugging in 0 for x of 2t dt, okay? Well, we know that that is actually 0 because there's no area, there can't be any area when you haven't traveled any distance, okay? So now let's try g of 1, okay? So g of 1 might be a little bit harder, okay? So what I'm going to do is I'm going to go from 0 to 1 of 2t dt, okay? So I'm going to graph this value here. So we're going to go from 0 to 1, okay? And let's see here. I believe we should get 2. No, g of 1 should be 1. Yeah. Let's see here. Okay, let me just double check. So I'm going to graph y of 2t right here, or y equals 2t. I'm going to just graph this real quick. Let me just graph this for you. And then so we get our line, and you guys get the idea. It's supposed to be a line. I can't draw though, okay? So this is our line right here, okay? Now the thing is that when we do this, we can basically say the definite integral. So we have to remember this idea. The definite integral stands for the area under the curve between the x-axis and the curve itself. So if I graph y equals 2t, this is what it would look like, okay? I can't stand that line. I'm going to try better. I guess I can't draw better. Okay. So we're there, okay? And we have 0 here, and then we go over 1, up 2, we go over 2, up 4, we go over 3, up 6, we go over 4, up 8, we go over 5, up 10, okay? Now the thing is that's the graph of that, but that is not what the integral of 2t stands for. The definite integral of 2t, or of 2x, or whatever you want to say, that integral stands for the area under the curve. So if I want to go from 0 to 2, this would be, oh, well, let me do this one first. Let me show you how I got this one. So what I would do with this one is I'm going to take and I'm going to go from 0 to 1, right, for this first guy right here. We're going to go from 0 to 1, and I'm going to put a point there, and I'm going to draw a little triangle, okay, and I'm going to shade that in. And that is now my triangle. Now that triangle, how do we find the area of that triangle? Well, it has 1/2, oops, let me write this in red. 1/2 base times height. Well, the base is 1, and the height is 2. So we get 1. So that's how I got 1 that last time. So now we're going to go from 0 to 2 of 2t dt. And once again, notice that it's g of x, and this is the x. So that's what I'm plugging in. I'm substituting in x for that, not into the t. Okay. So now let's do this next one. If I go over 2, my triangle would now go to here, right? And so we have that. Now what's the base of this new triangle? That base is 2. So we're going to do 1/2 base of 2 times the height of 4. So that would be what? 4, right? Now let's do another one. 0 to 3 of 2t dt. And this would be 1/2. Now we do this again. We go here to 3. Oops. We shade that in. And again, we're finding the area under the curve because that is what that stands for. That is what the definite integral stands for. It doesn't stand for the line 2t. It stands for the area under the curve. So that has now a base of 3 and a height of 6. So this would be 9. And then if we do 4, I hope you guys can see the pattern now. So notice it's 0, 1, 4, 9. What do you think the next one's going to be? It's going to be 16. And what would the next one be? It's going to be 25. So if I say g of 5, I know it's going to be 25. So I'm starting to get the feeling that all of the areas are perfect squares. That's the pattern that I'm recognizing over here. So what I'm going to do is I'm going to take another graph. Okay. But this time I'm going to plot these values that I got. Okay. So I'm going to plot, let me do 1, 2, 3, 4. And let me do it by 5 because they get big pretty quick, right? So let's go 5, 10, 15. Okay. So I'm going to graph this now, and I'm going to go, oops, this is 1, 2, 3, 4. So now I'm going to graph this, and it's going to go 0 is 0, right? So I'm going to plot right here, 0 and 0 for my area, right? And now I'm going to do 1 and 1. Okay, so no big deal. 1 and 1 would be like right about there, right? Now let's do 2 and 4. Well, that would be right about there. Now let's do 3 and 9. That would be right about there. And now let's do 4 and 16. That would be right about there. And then I'll do one more and just kind of eyeball it, 5 and 25. That would be like there. So if I did it correctly, it is no longer linear, right? This is the new shape I would get, okay? So now here's the thing, okay? What does this look like? These look like perfect squares, right? So what do you think I just graphed? Well, I feel like g of x should be, I think, x squared. And let's see if it would work. If I plug 1 in, I get 1. If I plug 2 in, I get 4. So I'm plugging it into here. If I plug 3 in, I get 9. If I plug 4 in, I get this. Now, the only thing is we only care about from 0 to whatever we say at x. That's why I only drew the right-hand side. But here's the thing. What if I want to know the area under the curve at any point? So let's now switch it up. Let's say not to there. Let's say I want to know the area under the curve from 2 to 5. And let's say I just want to know this area in blue right here. I don't want a complete triangle. Well, now I'd have to use a trapezoid or something like that. And I could still do it, and that's okay. But I could use this guy over here. I can use my new value over here to help me say what the value would be. And the way I would do it is I would find, now again, remember this graph, the g of x over here stands for area, right? This is a representative of areas under the curve. And we plotted a function that represents area. So that's kind of the catch, okay? And again, a function can represent whatever you want, right? So the thing is when we come back over here to this guy, how would I have found, if I wanted to know the area under the curve from 2 to 4, find the area from 2 to, let's go 5, I'm sorry, from 2 to 5. Okay, so what I would say is, well, I would find the big triangle, right? So the big triangle would be this whole thing. And that would have, so I'd say big triangle, you know what, I'll just write it as a symbol, big triangle minus little triangle. Okay, so the big triangle would have a base of 1/2, I'm sorry, 1/2 base, which would be 5, times the height, which would be 10, minus 1/2 the little triangle. Now the little triangle would just be right here, and we subtract that off, right? So we have to subtract off this little missing piece, right? The little piece in red. Okay, so we're going to subtract that off, and that would have a base of 2 and a height of 4. So now we're going to get what would that be? 25 minus 4. So we would get 21. And that's how we could find that area. Or what I could have done instead is I could have come over here and I could have just said, well, let me see, this one is 5. This is 5 right here, I guess. I kind of didn't draw it too good. And up here, so this is the 0.5 comma 25. So what I could have done is I could have just taken this point, and then I could have taken this point, and this is the 0.2 comma 4, right? And I could have subtracted their y values. So I could have just done 25 minus 4 would give me 21. That is the same as doing the areas. Now, why is that? It's because this function, once again, where did g of x come from? G of x came from graphing or plotting the area values for each of those rectangles or those triangles, okay? So that's the fundamental theorem of calculus. That's what it's kind of trying to show you. There's this relationship, okay? Now, how did we get these areas, okay? So it worked out nice because 2t is a very nice graphable, something easy to work with. And then when we cut it up into pieces, we know how to find those areas. But this is the motivation behind the fundamental theorem of calculus. This is kind of the idea behind it. This isn't a proof, once again. This is just trying to get you to see that, notice this straight line right here. So this is just a regular old line, right? 2t or 2x or 2m or whatever you want to say. It's a regular old line, and we graphed it right here. But when we plotted the area values, we got this function, we got this function here, okay, which is basically half of a parabola. So by integrating a line, we ended up with a parabola, but this parabola is something special. It's very specific. And once again, you know that this is the antiderivative, right? Because that's literally what integration does, is it uses the antiderivative, okay? So we basically just found that there is a relationship between the antiderivative and the areas under the curve, okay? So that's the idea that is kind of the groundwork for the fundamental theorem of calculus. Now, the fundamental theorem of calculus comes in 2 parts. Part 1 is kind of basically, how can I say this? Not to overgeneralize it, but it's basically trying to show you that the antiderivative and the derivative are in fact inverses of each other. And it's kind of giving you permission to treat them that way. Just like, if you have a radical, you can, if you have a square, you can square root it. If you have addition, you can subtract. If you have multiplication, you can divide. Well, in this sense, we have, if you want to get rid of a sine function, you can use an arc sine function because they're inverses of each other. So what this is trying to show you is just like with inverses, I guess what I was talking about before was inverse operations. And in a way, this is inverse operations too, but it's a little bit more powerful than that, because you're basically saying that you can undo a derivative with an antiderivative, or you can break down an antiderivative with a derivative. So they're basically giving you, with the fundamental theorem of calculus part 1, they're kind of giving you a free rein to do that. Now, there's always going to be things you have to be careful of, such as continuity and everything like that. And the function has to be defined on an interval. However, the fundamental theorem of calculus, it almost feels like you do nothing. If you're just applying it part 1, it doesn't feel like you're doing much, because it feels like a lot of times you're rewriting. But think about this: when you take f of f inverse of x, shouldn't you just get x, right? If they are in fact inverses each other, you shouldn't really do much to it. It should be what you started with, right? So That's what they want you to do with the fundamental theorem of calculus part 1. Okay, so we're going to spend much more time on part 2, but the foundation or the kind of the free pass to say now we can treat antiderivatives or integration as the opposite of differentiation in terms of inverse functions, not in terms of opposites. I'm sorry, I misspoke. More in terms of inverse operations. So part 1 says is if f of t is continuous on a closed interval a to b, then the function defined by g of x, and that's what we just did above, a to x, the integral a to x f of t dt is continuous on the closed interval a to b and differentiable on the open interval a to b with g prime of x equals to f of x. That is to say that the derivative ddx of the of the integral a to x of f of t dt is just f of x. So basically what you notice here is f of t becomes f of x. That's it, okay? That's what the fundamental theorem of calculus is telling you. So look what happens. Basically, the derivative and the antiderivative work against each other, and you're left with f of x, okay? So they just want you to kind of see that idea, that concept, that relationship between inverses, and just show you that this is how it would work, okay? So the lower limit must always be a constant, and the upper limit must be a variable like x, something similar to x. If it's ever something uglier than that, then you have to use u prime and stuff like that to account for it. And I think I have a formula for that in here. So it says find g prime of x if g of x is equal to the integral 2 to x t squared plus 3 dt. Okay, so take a minute. Is this a really, really tough problem, or is this actually a really, really nice problem? So think about it. If we go back up here, it says if g of x is this, then g prime of x would just be f of x. So look what's in here. You just rewrite it, but you change it from t to x, okay? So this literally, if I, and you could do it like this, you could ddx both sides, okay? Now the derivative of g of x is g prime of x, right? And then the derivative of the integral is just gonna be x squared plus 3, x squared plus 3, and that's it, that's g prime. And that's all there is to it. So notice it feels like we did nothing, okay? But that's just because it's the beginning, and that's just the fundamental theorem of calculus part 1 is, again, trying to get you to see this relationship and see how it can be worked, okay? So this next one, it says, oops, I left this one done. Sorry about that. So this next one is a little bit harder. So I want to kind of show you guys, what if there's ever something a little bit more than x? So this always must be a constant. So it says if g of x is equal to the integral a from a to u of x. Now remember, that's starting to mean something other than plain old x. So maybe it's like the sine of x or e to the x or something like that. Something not normal, or I shouldn't say not plain old x, of f of t dt. Then g prime is worth f of u of x times u prime of x, okay? So let's see what that means, okay? So basically we have to attach the chain just like we're used to doing. So notice we have our constant in this problem, and we have something other than plain old x here. So 3 to the x, t cubed dt. So what I'm gonna do is I'm gonna do just like before, I'm gonna ddx both sides, okay? So the left side will become g prime of x. Sorry guys, sore throat, or not sore throat, I'm sorry, I'm just my cough or something. So anyway, we have the derivative of this. Now the derivative of the integral is just going to be x cubed, right? So that's what we should have had. However, somebody messed up. It's not a plain old x. So we have to change this, and we have to realize whatever this is, f of u of x. Well, this is my f of, this is my f of t, right? So I have to plug in whatever my upper limit of integration is. So that's 3 to the x. So I'm going to take 3 to the x, and I'm going to cube it, okay? However, I then have to take the derivative of the inner function, my u prime right here. Now, what's the derivative of 3 to the x? That's one of the ugly ones. That's not the normal nice e to the x one. So this will be 3 to the x, but then you have to multiply by the ln of 3. So this is my u prime. This This is my u prime of x, okay? So if we want to clean it up even better, let's see. Well, this is e to the 3x times 3 to the x. So this would be what, 3x? So this would be 3 to the 4x ln of 3, natural log of 3, okay? Yep, and that's how you can do that problem. Now, what if they try to confuse you? Okay, what if they do not have the lower limit of integration starting at a constant, but they still have an x? Remember, we talked about this in the previous videos. We can rewrite this as g of x equals, and you can rearrange limits of integration and go from 1 to x, but the price you pay is the negative. So I fixed that situation. Now, once again, I'm going to ddx both sides. So this will now become g prime is equal to negative x squared. And that's it. That's all there is to it. Okay, so just be careful of that. I think I saw that in one of the homework problems where they gave you a limit of integration that wasn't in the right order and you have to fix it. Okay, so it's no big deal. So this is negative. Okay. And then this would be our answer to this one. So that's the fundamental theorem of calculus part 1. The one that we seem to use much more often in calculus because we care so much about the area under the curve. And again, the fundamental theorem of calculus is trying to get us to see that inverse relationship. But the fundamental theorem of calculus part 2 is where we do a lot of our heavy lifting in calculus. It's where we do a lot of calculations in calc 1, 2, and 3. Okay. So the fundamental theorem of calculus part 2 says if f of x is continuous on a closed interval a to b, then the integral from a to b of f of x dx, now notice this is not f of t, this is saying of f of x dx, is big F of b minus big F of a, where f of x is any antiderivative of f of x. That is to say, f prime of x is equal to f of x. So this right here is what I was showing you guys up here. You see how I did this? This was f of b minus f of a, okay? And this was a, and this was, oops, and this was b, okay? So that's what I was doing with those problems. And then when you find f of b, this is f of b, and this is f of a. And that's how I did it. So that relationship is now coming back here in the fundamental theorem of calculus part 2. Okay, let me scroll over here. So what this is saying is that if we can find the antiderivatives and then subtract the heights, so it's very important you understand. What they're saying is you are able to find the area under the curve of some function by calculating the heights of the antiderivative of that function and then subtracting them at those two locations, okay? So it's really important you understand that the graph or the area under the curve that you find, you don't actually shade it in and find that area yourself. You actually find the antiderivative of that function, which is some new function. And then that new function, you don't find the area under the curve of the new function. You simply find the heights of that function. And whatever those heights are, when you subtract them, you end up it becomes the area of the original function. That's what's happening here, okay? So I'm subtracting this height minus this height. That's this location here and this location here, and I'm subtracting those two. And it turns out that that area is this chunk right here. So this graph tells me the area under the curve of this graph. Okay, so that is the relationship. That is the big jump from the fundamental theorem of calculus. Is it saying that the antiderivatives can help you find the area under the curve of other graphs of their original functions? Okay, so we're going to come over here and practice this a little. And this is like going to become your bread and butter, guys. This is something you have to know how to do inside and out. This comes up in any calculus-based math that you're going to do. And again, it's called the fundamental theorem of calculus for a reason. Okay, so what I'm going to do is they asked me to find this area. Let me scroll out a little. So I'm going to find the area of 3x squared dx from 0 to 3. Now keep in mind, how would we have needed to do this before? We would have needed to do this, right? And that would be terrible. We don't want to have to always do that. So what we're going to do is we're going to learn this faster way. So we're going to use antiderivatives to help us find this instead of having to use the limit at infinity of Riemann sums. Okay. So what I'm going to do is I'm going to find the antiderivative of 3x squared. Well, I know the antiderivative of the antiderivative of 3x squared is equal to 3x cubed over 3. And then here's the way we're going to write it in our class. And you can either use these little hooks like that, or you can just use a line like that. Either one is fine. I've seen both. I've even seen parentheses as well, but I normally only use that with matrices and other things like that. So, and I'm going to put from 0 to 3. So I'm going to cancel that and cancel that. So let me just rewrite this for cleanliness. So this is from 0 to 3 of x cubed. Okay. So now what do I do? So normally, and just so you guys know, isn't it normally supposed to be like this? Aren't you supposed to do plus and minus? I'm sorry, you're always supposed to do a plus C when you do an antiderivative. Let me show you why the fundamental theorem of calculus, you don't do that. So I'll write it this time, and then I'm never going to write plus C on this again. Okay. So it says that we now do this. Big F of B minus big F of A. So that would be 3 cubed plus C minus 0 cubed plus C. Okay, so this is going to be 27 plus C minus C, and the C's will always cancel. So we do not have a plus C when we're doing the fundamental theorem of calculus. Now, what does this stand for? Now, just to be clear, this is a cubic. Okay, I just found a cubic, and I calculated the heights of that cubic. And then when I subtracted the heights at 3 and the heights at 0, it gave me this number 27. It turns out 27 is the area under the curve of 3x squared, which would be, a pretty steep parabola, right? And then from 0 to 3, so here's 0, here's 3. And if we calculated this area, that area would be 27. Okay, notice this graph right here, this is actually a graph of x cubed. X cubed would go like this, right? Two different graphs. You are not finding the area under this curve at all. What you are doing is you are finding this height here, and you're subtracting them. This turns out to be a height of 27. This is a height of 0. So that's a big distinction that you cannot lose track of, is you are finding the area under the curve of the original function, but you're using antiderivatives to help you find it so you don't have to do this, okay? So we get 27, and that 27 is the area under the curve. Okay, so let's look at another one. So now pause the video. You guys try to find the area under the curve of sine of x plus 1 dx, okay? From 0 to pi over 6. Pause the video and try to find the area of these two functions right here, okay? All right, so hopefully you guys are back. Now what you should have done is, again, you don't have to show me this step, but this is what you're actually doing. You are going from 0 to pi over 6 of sine of x dx plus the integral from 0 to pi over 6 of dx, or 1 dx, right? So you're splitting it. I'm splitting it as two separate integrals. Now, I don't require you to show me that particular step. If it's something very involved and you have to show it to me, you'll know the problem will be much more difficult than this. What you can choose to do is you can integrate this and you can integrate this. So the integral of sine is negative cosine. How do I know? Because what's the derivative of cosine? It would be negative sine. So how are we going to get back to a positive? I had to throw a negative in front. Okay, so now I'm going to integrate 1, and the integral of 1 is x. And then I'm going from 0 to pi over 6. So now I'm going to do from f of b minus f of a. So this will be negative cosine of pi over 6 plus pi over 6 minus negative cosine of 0 plus 0. Now remember, just to be clear, this is big F of b, my antiderivative evaluated at b, and this is big F of a, my antiderivative evaluated at a. So let's see what we get here. So we know the cosine of pi over 6 is going to be square root 3 over 2 plus pi over 6. Now a minus becomes a plus, and the cosine of 0 is 1. So I'm going to say plus 1 and then minus 0. So this would be my answer. I don't feel like cleaning this up is ever going to do any better because the square root of 3, the pi, and the 1 all cannot combine like terms. They're all different irrational. Well, two of them are irrational numbers. So let's just go with that as our answer. I don't think there's much cleanup for that problem. Okay. Yeah, that's that one. Okay. So now hopefully you guys have this one. And again, you guys in general, I don't want decimal answers because that tells me you just plugged it in on your calculator. Your calculator does have an integration feature that you can use to check your work, but I need to see the work. If you give me a decimal on this particular problem, I'm assuming you didn't know how to do it and you just hit enter on your calculator. So for definite integrals specifically, or in general, you always have to show the step right here. Okay. It always has to be shown. I need to see that so I can see your work. Okay. Now we come down here. We don't know how to do the antiderivative or the definite integral of a quotient. So what I need to do is see if there's algebra that I can do first. So I'm going to rewrite this. This will be from 1 to 2 of 6y squared plus 5y dy, right? So I just divided everything by y. So I got 6y squared plus 5y. So now this is going to be 6y cubed over 3 plus 5y squared over 2. I'm just doing the antiderivative from 1 to 2. So once again, f of b minus f of a. So this would be what? 2 over 1. So this would be what? 2 times 2 cubed. So this would be what? 16. And that would be what? 10 minus this would be 2 plus 5 halves. Let's see here. Okay, so that would be 26. Well, that'd be 24 plus 5 halves. So if this is a nice decimal, so I guess we could do this one. 26.5. Let me just double check and make sure I did it correct. I actually don't have that one written down for whatever reason. So let's see here. 21.5. Oh, it's a minus 2. Yep, I thought there was something wrong with that. Okay, so let's go over here. Oh yeah, minus 2, not plus 2. So this is 26. Oh, and it's minus the 5 halves as well. That's what messed me up. Yeah, it's a silly mistake. So this is actually what, 4.5? So 26 minus 4.5 would equal 21.5. There we go. Yeah, sorry about that. I thought it looked a little suspicious. Okay, so now one more. Again, we don't know how to do a product. So what we have to do first is we have to do a rewrite. Let's distribute the square root of x. We don't know how to do the product. I'm going to teach you that in Calculus 2, or if you take me for Calculus 2. So this is from 0 to 1. Since I can't use the product rule, or we haven't learned how to undo the product rule, I'm just going to distribute. So this will be x to the 3 halves times 7x, oops, not times, plus 7x to the 1/2 dx. And do not forget to write the dx, okay? You need it on these problems. It's part of the notation, but it also will come in handy in u substitution. Okay, so now we integrate. So this would become what? Add 1 to the power, we get x to the 5 halves divided by 5 halves, plus 7x to the 3 halves divided by 3 halves, from 0 to 1. So let's do a little cleanup. This would be 2/5 x to the 5 halves plus 2/3, oops, not 2/3, 14/3 x to the 3 halves from 0 to 1. Thank goodness that it's from 0 to 1, right? Otherwise it'd be really annoying. So this is going to be 2/5 plus 14/3, because I plug 1 in and it doesn't do anything, minus 0 plus 0, right? Because when I plug 0 in. And then once again, this is my big F of B, and this is my big F of A. And this is my B, and this is my A. Okay, so then we end up with, let's see here, 2/5. This will be a little bit of times 3 times 3. This will be times 5 times 5. So let's see here, that's 6 plus, what is that, 70? So 76 over 15, I believe. Let me just make sure once again. Yep, 76 over 15. So let's go back here. Okay, so that's another good one. All right. So now, is that the last of them? Let me see if I have one more. Oh yeah, I have two more that I'd like to talk to you guys about. Or maybe three. So let's do another example. So determine the integral from -1 to 3 of 1 over x squared dx. Okay, so I'd like you to find the area under the curve of 1 over x squared from -1 to 3 dx. Okay, so when we're doing this problem, pause the video, and I just want to see what you guys come up with, and then you can talk to me about it. Okay, so hopefully you guys unpause the video, and the problem is many of you may have gotten this. I think many of you might have gotten -4/3. Okay, this is the wrong answer. What was the first rule of the definite integral? So let's go back up here to the fundamental theorem of calculus part 2. It says if f of x is continuous on a to b, then you're allowed to do this. Is this function continuous on a to b? Well, from -1 to 3, that means that you're dealing with this graph, right? 1 over x squared looks like this, or some variation of that. Sorry about that. Oops. Oh my gosh, I hate it when I can't draw, you guys. Oh my goodness. Okay, hold on. Well, you get the idea, but okay, so that's 1 over x squared. That's a horrible 1 over x squared, but you get the idea. The problem is 0. There is a vertical asymptote at x equals 0. So that means there is a discontinuity at x equals 0, and x equals 0 is definitely in this interval from -1 to 3. So for this course, we could not integrate this. We would say we cannot integrate this, and we're done. Okay, we can't do it. Next semester, I'll teach you how to do this problem. So, and it turns out we will get -4/3, I'm pretty sure, but next semester I will teach you how to do this problem. Okay, or not this particular one, but integrating over discontinuities or asymptotes, so to speak. So we'll talk about that in chapter 7.8, improper integrals. But for now, this problem we can't do. Okay, so I want to look at one more. Okay, I want to look at one more, and it's a piecewise function. So it says find the integral from 0 to 3 of f of x dx for f of x equal to, f of x, sorry, defined below. So let me give you what f of x is defined as. So f of x is defined as the piecewise function, piecewise defined function 3 when 0 is less than or equal to x is less than or equal to 1, and 3x squared when 1 is less than or equal to x is less than or equal to 3. Okay, so here we have a piecewise function, and I want you to integrate this. Okay, so the thing is I'm going to end up needing to split this into two integrals. Okay, so I'm going to first integrate. I'm going to integrate from 0 to 1 because they told us this is the domain of this portion. That's the restriction put on that portion. So from 0 to 1 of 3 dx. Okay, and this will be the integral from 0 to 3 of f of x dx. Okay, let me write this a little cleaner. So the integral from 0 to 3 of f of x dx is going to be the split of these two integrals added. So plus the integral from 1 to 3, right? So now I'm doing this domain restriction, but I got to use 3x squared. So this would be 3x squared dx. So let's see what that is. So this will become 3x from 0 to 1 plus this would be what, 3x cubed over 3. So this would just be x cubed from 1 to 3. So let's do the calculations. This would be 3 minus 0. Hold on. Yeah, f of b minus f of a would be 3 minus 0. So that's that. Plus, this would be 27 minus 1. So then this would be 3 plus 26 would be 29. Okay. And that is our area under the curve of this function, which is comprised of this piecewise, or is made up of this piecewise function. So piecewise can also be done, but normally you have to do it as two separate integrals using the domain restrictions. Okay. So I think that's it for the fundamental theorem of calculus and working with these definite integrals. The next section will be on indefinite integrals, which are, you already technically did them in the section on antiderivatives. That's what an indefinite integral basically is. So you've already done it. So it's a really nice section and it should be kind of review for many of you. Okay, but that'll do it for this section. Thanks for watching, you guys. See you in class.